In this video, we're going to take a look at something called collision theory. So before we get into collision theory, we first need to refresh our memories about what kinetic molecular theory is, because this is helpful for us to understand what is going on in collision theory. So kinetic molecular theory says that ideal gases are a collection of randomly moving particles that collide elastically. So we've got these randomly moving gas particles in our sample here. The average kinetic energy of a gas of gas particles is proportional to the absolute temperature of the gas. And as temperature goes up, the kinetic energy is going to go up. So the particles are going to move faster. So the particles will move faster. And that's kind of intuitive, right? The more energy we give something, the faster it will move. Particles can also exchange energy with one another through collisions. And so this is really important for collision theory. So collision theory says that essentially for a chemical reaction to occur, the following conditions must be satisfied. First off, two or more particles must collide with each other. The colliding particles must have the correct mutual orientation, and the sum of kinetic energies of the particles must be sufficient to initiate the reaction. So if you take this reaction here, we have carbon monoxide reacting with oxygen gas. And you have the particles colliding, but say they collide at the right orientation, but there's not enough energy here to initiate the reaction, then no reaction is going to happen. But if we get them colliding at the right orientation and the right energy, then a chemical reaction will occur and will create our products here. So essentially, for a chemical reaction to occur, we have to have colliding particles have the right orientation and sufficient energy to create that chemical reaction. We have a term then for the minimum kinetic energy that is required for a chemical reaction to occur, and this is called our activation energy, or we use E with a subscript A to represent activation energy. So as I said, this is the minimum kinetic energy of colliding particles that is required for a reaction to occur. If you've ever done like mini golfing or whatever, and say you had this hill here, you can think of, when you're hitting this ball, what's the minimum amount of energy you have to hit that ball in order to get it over this hump so that you can get it in the hole at the end. So that's essentially what activation energy is how much energy we need to just get it to tip over to the next side. So this idea with collision theory and activation energy can be represented in energy profiles. So I have an energy profile here shown for an exothermic as well as an endothermic reaction. On our axes here, we've got energy, and then we have reaction coordinate. This is just kind of like the progress of the reaction. So progress of the reaction. Fancy way of saying that. So for an exothermic reaction, our reactants typically have more energy than our products, giving us a delta H enthalpy value that's less than 0 for the reaction. And if we look at the activation energy here, it's this hump that we need to get over. So the energy profile includes that hump of energy that we need to get over, and the value between the reactants and the peak of this particular graph is going to be our activation energy. Now, at the peak here is something called our transition state. So the transition state essentially is the least stable arrangement of the atoms in the reacting species. In this state, some of the chemical bonds in the reactants are broken or weakened, while the new bonds have not fully formed. So it's kind of in the middle between the reactants and the products. If you look at an endothermic reaction, you can see here just the differences. The reactants are lower energy than the products. our delta H enthalpy value is positive. And then if we're looking at the difference from the reactants to our peak, that is our activation energy. So that's for the forward reaction. If we were to look at the reverse reaction, you could take it from the products and go up here. So in an endothermic reaction, a reverse reaction would have a lower activation energy. And in an exothermic reaction, the reverse reaction would have a higher activation energy. So that's it for collision theory. That's how we relate it to energy profiles. That's it for this video then. We'll see you in the next one.